Okay, so let's just start today's lecture. Okay, so today we are going to kind of continue our analysis for the Laplace transforms. Okay, so in order to do that, I would like to kind of recall our transform table. Okay, so we have a transform table which you have already seen on your I mean, you will see or you have already seen and you will see. Okay, so on our exams, that is usually attached to the last page of our exam paper. Okay, so it's usually attached to the last page of the exam paper. Is the short table of Laplace transforms. Okay, so this is the short table of the Laplace transforms. Okay, so we have been kind of studying this table in a certain sense, line by line. Okay, and we have seen many lines of this table, and now so I would like to have an announcement for the future of these lectures is that we're going to go through the whole table. Okay, so in particular, you can see that several lines of the table has been kind of thoroughly investigated. For example, line 11 and line 16 consists of what we call it the shift table of Laplace transforms, right? So they are going to tell you how the shifts in Laplace transforms can be done either from the forward side or from the backward side, right? So that's kind of very important. Now, for the rest of these few lectures, okay, so for the rest of these few lectures of this chapter, we're going to kind of focus on line 18, 19, and 20. Okay, so these are kind of, so first of all, it's not clear what this pi ABT does, what does it mean? And it's not clear what does this delta t minus a mean, right? So, but it's clear what this ut minus a mean, right? So the ut minus a is simply a step function, right? So as we have been talking about such step functions, right? So basically the ut minus a is such a function, so ut minus a is such a function that at point A and before point A, it was 0, and then it becomes 1 after point A and on, right? So that's kind of what we've been talking about for the unit step functions, right? So the 17 is good, but then the 18 and 20 isn't clear at all. Is that good for everybody? Okay, so for the 19, the f and g should correspond to capital F and capital G in Laplace transform. So the notations in 19 is clear, yet the proof of 19 is not clear at all. Okay, so that's a kind of, we're going to kind of focus on these 3 lines of the Laplace transform table for the rest of this chapter. Okay, so that's kind of the announcement of what we are going to do. So for today, we're going to kind of look at 18 and 20. So we're going to kind of be talking about the impulse functions. Okay, so we're going to talk about the impulse function. So what is an impulse function? Well, imagine that we've been talking about the problems related to vibrations, right? So let's say impulse function. Okay, so right, so we have been talking about the problems related to vibrations. So the vibrations corresponding to such problems, okay, so vibrations corresponding to such problem, mu double dot plus gamma of u dot plus k of u is equal to the external force, right? So this is kind of models the oscillation of a certain mass attached to a spring. Let's say u is the relative displacement with respect to the equilibrium position, right? So as a review, you must realize that m is the so-called mass, gamma is the so-called damping constant, right? So gamma is the so-called damping constant, and k is the so-called Hooke's constant, right? So Hooke's constant corresponding to the resistance force, proportionality constant for the resistance force in the spring. And the external forcing is Fe of t, okay? So external force, right? So this kind of describes the motion of a certain mass, let's say attached to a spring, right? So and they started to oscillate. Okay, so let's describe its oscillative motion. So now, in order to kind of model everything more concretely, think of experiments, right? So think of the actual experiments that happens in your labs, right? So usually we take, so for example, as a resonance case, we're going to take the forcing as a periodic function, right? So let's say with a certain magnitude f0 and with a certain frequency omega, we're going to use the function f0 cosine omega t, or maybe we're going to use f0 sine omega t, right? So, but these are continuous forces. It means the forces are going to be constantly acting on the mass. What about the kicks, right? So the kicks are more vivid, right? So let's say when the motion, okay, so when the mass is oscillating, okay, so let's say when the mass is oscillating, right? So suppose the mass is oscillating, and then at some moment you just suddenly kick, right? So you're going to just suddenly kick this mass and give it a sudden movement, and then you're going to take your force away. So that's called kicks. It's a good family, right? So, and then we want to understand, okay, so then we want to understand what happens, right? So then we want to understand, let's say, what happens to the vibration subject to a kick, right? Suppose your mass is kind of freely vibrating, but you suddenly kick it. Then is the trajectory going to move, right? So are you going to have a different trajectory for the motion of the mass, right? So that's kind of a very interesting problem, which means that you're going to model, okay? So we're going to kind of model, okay? So model kick force. So that's kind of very important. We want to kind of model kick forces. So what does the kick forces? How does kick forces look like, right? So now think of a soccer ball, right? So think of let's say American soccer ball, right? So or maybe let's say think of a British football, right? So if you have a football, right? So let's say you're playing on the ground, right? So certain player is playing on the ground and he's kind of hitting the football. This is the football, okay? So now, what does the football process goes? Well, your hand, your feet, the foot of this person is going to touch the football, but then he's going to immediately. So the next stage is that he's going to kind of immediately take his foot away, right? So and then the football started to gain a certain momentum. It started to move. Is a good fabric. So this is like a very typical. This is like a very typical shape of kick forces, right? So that means the force is not going to kind of stay there for long, but the interaction, right? So the interaction time between the foot and the ball is very short, and then just after this short time, a certain momentum is going to be given, right? So a certain momentum is going to be given to the ball, and it gains a certain velocity v and started to move. Is that good for everybody? Okay, so this is a typical kick force, right? So this is a typical kick force. So how do we think of it mathematically? Well, this mathematically, we're going to think of impulse type force, right? So that's that's kind of what we will be thinking. Okay, so we're going to think about impulses, right? So what does impulse mean? Well, impulses are going to kind of vividly describe the interaction process. For example, for the football player, just as in this picture. So what it means is that let's say before a time A, right? So before a time A, the force, the interaction of the foot with the ball didn't happen, right? So, but starting from point A, there's going to be some F0, right? So let's say starting from point A, the force is going to look like F0, and then it interacts with the ball for a certain period of time until you reach the point B. You're going to take away your foot. The interactions just stops. So this kind of describes the external forcing. Is that good for everybody? So you can see that the situation is not exactly like the unit step function, but indeed we can actually say that the external forcing is nothing but the F0 multiplied by UA of t minus the UB of t. So it's kind of the difference between two unit step function. Why is that the case? Because if you think of UA and UB, then they're going to look like this, right? So UA of t, or maybe I will write it as UT minus A, right? So let's say this is the point A, then the UA of t is something like this. And what about UB of t? Well, the UB of t is UT minus B, and then the force is going to be something like this. So at point B, it's going to be 0, and then you starting from B on, it's going to be 1. Is a good family. So what happened here is that if you use the first function, subtract the second function, then it means that before point B, I mean, this is A, the second function is going to be 0, first function is 1, so you're going to create a 1. But after B on, everything is going to be moved back to 0. So basically, I should have an open interval here. Let's say it doesn't quite matter because it only happens at points, but let's be precise. It should be something like this. Right, so that's going to be like f0 of u of t minus a minus the u of t minus b. So this is kind of what happens to such impulses that we can describe from the football example, right? So from the football example. So that's kind of impulses. Okay, so now these kind of impulse functions are exactly what you see here. Okay, so the pi ab of t is nothing but this function. So basically, we're going to set this up. So we're going to set this pi ab of t to be the u of t minus a minus the u of t minus b. Let's say a is less than b, something like this. Okay, so that's going to be our pi ab of t. Okay, so this is going to be our pi ab of t. So therefore, you can see that the Laplace transform of this pi ab of t is easy to be calculated because of the linearity of Laplace transform is nothing but ut minus a minus the Laplace transform of ut minus b. So that's going to be kind of, if you still remember, or if you don't remember, it doesn't matter. You just realize that here the ut minus a is transformed to e power minus as over s. So that's going to give you e power minus as over s minus e power minus bs over s. So indeed, your result is e power minus as minus e power minus bs over s, and this is exactly what happens on this table, right? So e power minus as minus e power bs. So that's kind of settles line 18. Is a good family. So we have no problem regarding line 18 now. It is kind of completely settled, and we understand what it happens. Is a good family? Okay. So therefore, for the rest of this story, we just need to fix line 19 and 20. So we're going to fix 20 today and for the next lecture, and then 19 we will occupy 2 more lectures. Is that good, family? Okay, so that's going to be the plan for our lectures. So let's kind of look back at this impulse function. Okay, so we were supposing that the impulse function happens starting from time A until time B. But usually, you see, when you play football, right? So when you play football, let's say British football, right? So you kick your foot is going to kick the ball, but the kick is not going to happen for long, right? So the impulse is or when you model the kick, it's not going to last for a very long time, but it's going to be a very short amount of time. So that means the b minus a is somehow short. So how are we going to describe it? Well, we're going to kind of find the center of this motion. So basically what I'm saying is that let's say there is a point t0. Okay, so let's say roughly speaking, we're going to say the kick force. Okay, so the impulse function, the kick force happens. Okay, so let's say it happens at time t0. And what does it mean? Well, it means that there is going to be a t0 minus tau, which serves as your A, and there is going to be a t0 plus tau, which serves as your B. Is that good, family? Okay, so what happens there is that your force is going to be just lasting from t0 minus tau to t0 plus tau. It will be a very short amount of time if tau is small. Let's say tau is small, right? So if tau is small, the force is going to just last for, so the force, okay, so the kick force, right? So the impulse force or kick force, right? So kick force only lasts, right? So only lasts for 2 tau amount of time, right? So this tau is very small. So So that's kind of more precise situation, more close to practice, because we're going to kind of fix our time to be at t0, and you just say, I kick the ball at time t0, which means that there is a small window. Okay, there is a small window of time during which you're interacting with the ball, right? So that's t0 minus tau serves as the previous a, and t0 plus tau serves as the previous b. Is that good for everybody? Okay, so let's say we're going to use this model. So then you can see that, okay, so then you can see that, let me suppose the force is of magnitude, right? So magnitude is L. Then you can see that how much, let's say, how much initial velocity is going to happen to the ball. Well, there's in physics, in your physics classes, we have the basic principle of impulses, right? So what is the basic principle of impulses? Impulses means that the momentum, right? So the momentum is equal to the impulse. So this is what we learned in our physics classes, right? So we say the momentum is equal to the impulse. So how do you calculate the momentum? Momentum is m of the initial velocity. M is the mass, let's say, of the ball, right? So let's say, so I'm going to just use, let's say, mu initial velocity multiplied by the initial velocity, right? So let's say the mu is the is the mass of the ball, right? So let's say the ball has mass mu. Is that good for everybody? Okay, so this is momentum. Momentum is equal to impulse. What's the impulse? Well, impulse is the magnitude of the force multiplied by the amount of time. So there's amount of time that you interact with the ball is 2 tau. So the impulse is nothing but the area under the shape of the function of the impulses. Is that good for everybody? So this is what you learned in your standard classes for physics. Is that good for everybody? Okay, so that's going to be the impulse. Right, so that's going to be the impulse theory, right? Impulse principle is a good fabric. So let me say, okay, so let me say we're going to ask the following question. Okay, so the impulse is, so basically what I'm saying that the total impulse is the integral of the force on the time, but the force is equal to a constant. So that's going to be just 2 tau multiplied by L. Is a good fabric. Okay. So now let me ask a reverse question. Okay, so let me ask a reverse question. For what kind of impulses? Okay, so what's the magnitude of impulse such that the momentum gain is 1? So basically, that means I want the initial momentum for the ball to be uniform, right? So it's going to be 1. So that means the momentum is going to be just fixed to be 1. Then you get a kind of a nice relation between the magnitude of the impulse as well as the time. So basically, it means that 2 tau L is equal to 1. You get such a nice relation between the magnitude of the force as well as the interaction time. So what does this picture say? Well, this formula basically is going to kind of give you the following. Okay, so it's going to kind of give you the following picture, right? So the picture is the following. So if you want, so let me say, okay, so let me say, first of all, I'm not going to kind of work with T0 because it's enough kind of shift T0 to be the origin. It doesn't quite matter, right? So I can say the impulse happens at 0.0, which means that from minus tau to tau, you're going to be working with this. You're going to be interacting with the force, with the ball. Is that good, family? Okay. So then you can see that 2 tau L equal to 1 simply means that the magnitude of this force is kind of going to be a height of 1 over 2L. So basically, it tells you that L is equal to 1 over 2L. Right, so that's going to be the height, and the external forcing in this scenario is going to be the function 1 over 2L if 1 over 2 tau if the time is between minus tau and equal to tau, and it is 0 if otherwise. So you're going to have something like this. Is that good, family? Okay, so that's kind of 1 over 2 tau. Now imagine, okay, now comes the real physics. Okay, so now comes the real physics. You imagine, okay, so imagine that the kick force, right? So everybody has such an intuition or experience that if you use your, let's say, use your foot, you hit the wall, right? So let's say the wall very heavily, right? So you suddenly hit the wall. Then the faster, okay, so the quicker you're going to hit the wall, the more pain you get, right? So why is that the case? Well, it's very simple, because if you want to normalize the momentum to be 1, and let's say you kind of made the tau to be half of the original time. So that means your interaction with the ball, right? So let's say your foot interacts with ball only at a half amount of time. Then what you need is like you have to double the magnitude of the force. Is that good, family? Then you have to double the magnitude of the force, because you just want to kind of have a half amount of time. But if you kind of double the amount of time, then you're going to have a much lower force. This is going to be half the amount of force. Is that good, family? So you have kind of a dynamical relation between the interaction time and the magnitude of the force. Is a good, family? Okay, so this is kind of going to be pretty interesting, because what actually happened here. So actually, okay, so actually in physics, let's say we're going to set tau equal to 0, because the interaction time is kind of modeled to be sudden. So that means you're going to kind of suddenly hit the ball and gives it the initial velocity, and then the football is going to move. So in that case, you can see that the tau becomes smaller and smaller. So basically, your force is going to be larger and larger, but it will be kind of only on a smaller and smaller set. So basically, you're going to have a picture of a certain spike, right? So you're going to have like the dynamical picture of a spike as you kind of go smaller and smaller. You're going to have a very spike function that hits the kind of infinity from here. So it's hard for me to draw it. Is that good, family? Okay, so that's kind of what we're going to happen for the impulse functions, right? So basically we're going to kind of set, right? So we're going to set, okay, so we're going to set, so basically what I'm saying here is that we're going to set the function d tau of t. It is going to be equal to 1/2 tau if let's say minus tau less or equal to t less or equal to tau, and 0 if otherwise. Okay, so basically, the d tau of t is such a function that has a magnitude, right? So let's say from minus tau to tau, the magnitude height is 1/2 tau. You're going to have a step, and then besides, it will be just jump to 0. So that's the function d tau of t. And then, but we need, okay, so, but we need, right? So, but what we need? Well, what we need is the limit, right? So, but what we need is the limit as tau goes to 0 of d tau of t. We're going to denote this function as delta of t. So you can see what's the limit goes. Well, the limit is just describes the previous dynamical process that I was describing before. So that means in the limit, you can see that previously you were having a d tau of t, but you're going to set tau to be small. So let's say if tau is being halved, then the d tau of t is going to be kind of larger. But tau goes to 0, you're going to see something that kind of is becoming 0 everywhere else besides 0.0. So that's going to be something like this. Is that good for everybody? Okay, so this kind of function, so basically you can see that the delta of t is equal to 0 if t is not equal to 0. Because everywhere not equal to 0, when tau is small enough, it will not be covered by the interval from minus tau to tau. But it is going to be infinity, let's say plus infinity, right? So it is going to be plus infinity if t is just equal to 0, because the at 0, the magnitude of the force is going to be larger and larger until you reach infinity. Is that good for everybody? Okay, so you have such a function. So it looks quite absurd function because it's just 0 and infinity, and it's defined by infinity. If you define a function to be infinity at a point, it means you define nothing, right? So it doesn't mean anything, right? So it's kind of quite a weird object, right? So it's kind of quite a weird object that you don't understand what really happens, but it indeed happens. So this is the function that we're going to kind of name it. Okay, so this is a function that we're going to name it as the so-called unit impulse function. Okay, so the unit impulse function. Okay, so this is what we call the unit impulse function. Sometimes it's also called Dirac's delta function. Okay, so the Dirac is a kind of a British mathematician and a physicist, a very famous theoretical physicist who has made important contributions to quantum mechanics, right? So when he studies the, let's say, when he studies the electrons, okay, so then he wants to model like the point electrons, and therefore he has to introduce this delta function. That's how delta function comes out. Okay, so now in order for you to gain a more vivid picture of what happens to the delta function, I would like to kind of show you an animation. Okay, so I would like to show you an animation from Wikipedia. Okay, so let's say delta function. Okay, so let's try to search for the delta function. So basically what I want to see is a dynamical process. When the interaction time becomes smaller and smaller, the magnitude of the force is becoming larger and larger. Okay, so let's say we want to take a look at this. Okay, so let's see. Okay, so okay, so we're going to look at the delta function. Okay, so we're going to look at the delta function. Okay, so we're going to kind of look at the delta function and see what's going on there. Okay, so yeah, so let's look at the delta function. Okay, so the delta function, Dirac's, you see, it was named after this physicist, Dirac. Okay, so that's Dirac observed such a delta function. So here is a good animation that shows like how this function gradually becomes more and more like a spike, right? So that was what I was just trying to describe. As your interaction time becomes smaller and smaller, the magnitude of the force is becoming larger and larger until it reaches infinity. And in the limit, we call this function Dirac's delta function. So that's kind of a nice picture and animation for the Dirac's delta function. Okay, so that's a nice animation for the Dirac's delta function. So let's come back to our lecture, right? So we're going to take this unit impulse function. However, according to this definition, it looks like we have been doing nothing, right? So you're just introducing a function that's zero everywhere else except the point zero. And at point zero, it's even not defined, it becomes infinity. So it looks like a very weird function, but it's not enough. Because this infinity, you can see that when you talk about infinities, right? So let's say when we talk about infinities, we can say that the infinity is the limit as t goes to 0 of 1 over t, or you can say 1 over t squared, or you can say 1 over logarithm of t, etc. So infinity does have an order, right? So let's say the order of infinity, right? So the infinity is not something that you can just talk about, but you have to specify which infinity you're talking about. So what happens to Dirac's function? Well, remember, okay, so remember that if you look, okay, so let's say, let me start a new page. Okay, so if you look at this d function, right? So what is the area under the function d? Well, that's just as we described. Because of the impulse principle, the momentum is equal to the impulse, but we have unified momentum to be 1, right? So that's kind of easily to see from the definition of the d tau, that you're going to see that the infinity plus infinity minus infinity integrated up to plus infinity of the d tau of t is just equal to 1, no matter what tau you do. Is a good family, right? So it's kind of very simple. But then you can see that if the limit happens, then you're going to see that from minus infinity to plus infinity of the delta of t. Okay, so let's say d tau t dt, right? So let's say d tau t dt is 1. Delta t dt is also equal to 1. Is a good family. So the infinity here is not just defined by an infinity, but it has to be specified by the fact that the delta of t, if you integrate from minus infinity to infinity, the integral is always being uniformed as 1. So that's going to be very important. Is a good family. Okay, so that means indeed the delta function is defined by 2 different criteria. First criteria says that the delta function is 0 if t is not equal to 0, it's infinity at point 0. but then the integral of the delta function on the whole interval is going to serve as a unit 1. Is a good family? Okay, so this is a good unit step function, unit impulse function. Is a good family? Okay, so that's going to be the unit impulse function that we're going to talk about. Okay, so let's say definition, right? So what is a unit impulse function, right? So unit impulse function, the unit impulse function is going to be defined as the delta of t is going to be equal to 0 if t is not equal to 0, and infinity if t is equal to 0. But there is another condition saying that the integral delta t dt on the whole interval has to be equal to 1. This is going to be very important. Is that good, family? Okay. So now let's come back to the initial question that we have been starting this lecture. We want to model vibrations, and we want to model the external forcing of the vibration as a kicks. So now we have a good candidate for the kicks. You're going to say that the kicks, so basically that the kicks are going to be modeled as an external forcing that's happening. Okay, so let's say it's F0 is the magnitude multiplied by delta of t. Is a good family. So what does it mean? It means that it's kind of F0 times the units impulse. So the impulse happens at 0, it means the kick happens at 0. But usually in practice, the kick is not going to happen at 0, it's going to happen t0. Is a good family? Okay, so that's kind of very simple because the unit step function, as you can imagine, is going to be something like a spike, but at point 0. So if you want the spike, like the impulse to happen at t0, it's just suffices to move the unit step function to this t0. So you're going to consider delta of t minus t0. Is that good, family? Okay, so that's kind of a solution to our problem, like how you model vibrations subject to sudden kicks. So that's kind of very interesting when you kind of play your equipment, right? So let's say in an experiment, you do an oscillation, but you suddenly kick it, then you can use this force, right? So now comes our original question. What's the original question? Original question is, let's say if you have a certain mass is kind of freely vibrating, and you suddenly kick it, are you going to change the trajectory? How are you going to change the trajectory? It means that you want to solve a differential equation. So this kind of tells you up to this level of these lectures, you kind of started to realize the power of differential equation because it gives you the modeling and predictive power. So basically we want to solve such differential equation, mu double dot plus gamma u dot plus k of u external forcing is something like F0 multiplied by delta t minus t0. Is a good family, right? So, and it can also be following function plus it can be even more complicated. Let's say it can become f of t multiplied by delta of t minus t0. So that's kind of a general function multiplied by delta. Is a good family. So we are going to kind of look at these two equations. So how are we going to solve them? Well, we're going to solve them by Laplace transforms, right? So because our chapter is going to talk about Laplace transforms. Right, so now how are we going to do Laplace transforms? Well, you're going to kind of Laplace transform the left side of this equation is mu double dot. So you Laplace transform it, right? So plus gamma u dot plus k of u is equal to F0 can be pulled out. Then you're going to just work with Laplace transform of delta t minus t0. Is that good, family? Okay, so that's a very simple Laplace transform that you're just looking at. Is that good, family? Okay. And then the Laplace transform of u double dot basically is equal to what? It's equal to s squared Laplace transform of u minus s of u of 0, right? So minus the u prime of 0, right? So that's what happens. And Laplace transform of u dot is s Laplace transform of u minus the u of 0. So you're going to get everything about Laplace transforms. The only thing you don't know is what is Laplace transform of delta t minus t0. And indeed, this is kind of covered in line 20, right? So here the t0 is just replaced by a. It tells you that the Laplace transform of delta t minus a is equal to e power minus as. Is that good, family? Okay, so that's kind of what we want to cover. So after this long story, now we have finished this story. It tells us that the delta function is going to be transformed under the Laplace transform into an exponential e power minus as. Is a good family? Okay, so that's kind of a nice picture. So So basically, the conclusion is that the Laplace transform of delta t minus t0 is going to be e power minus t0 multiplied by s, which is now as, is a good family. But how do you calculate it? Well, you can see that the Laplace transform of delta t minus t0 is nothing but the integral, according to the definition of Laplace transform, is 0 to infinity e power s and t multiplied by delta t minus t0 of dt. So this is kind of very important for our previous lectures. This is the definition of Laplace transform. Is a good family? But with this definition of Laplace transform, what can you really do? Right? So what can you really do with respect to this definition of this Laplace transform? Is a good family? But you can see that what is the delta? Well, we have been introducing the function d tau of t. It is going to be equal to 0 if it is going to be equal to 1 over 2 tau if minus tau less or equal to t less or equal to tau, and it's equal 0 if otherwise, right? So that's kind of what we talk about d tau of t. So the delta is nothing but the limit of d tau of t. So that's kind of being said. Okay, so that's kind of being said. First of all, we can kind of do a change of variable. So we're going to change the t minus t0 to be your new variable. So that's going to be said. Let's say this is e minus t s t minus t0, right? So multiply by e power. Okay, so let me multiply it on the left, right? So I'm going to kind of multiply it by e power minus s t0, right? So multiply by this one, delta t minus t0 dt is a good favorite, right? So if that is the case, you can see that because the delta function is going to be 0, right? So it's going to be 0 just except the point 0. So that means if t is not equal to 0, t0 is you're not going to contribute. So there's nothing but e power s t0 integral of e power s and t multiplied by delta of t dt. You just want to take a look at this function. Is a good family. But what is this limit? Well, this one you can see that this is nothing but st0 as the limit as tau goes to 0 of the integral 0 to infinity e power s and t multiplied by 1 over 2 tau of, okay, sorry. So I will not use 1 over 2 tau. I will use the d tau of t dt. Is a good family because the d tau of t, so basically I use the fact that the delta function is the limit as tau goes to 0 of d tau of t. So I can take a limit. So what's this limit? Well, this limit, you can see that it is a limit of a certain function, d tau of t, right? So what happened here is that the d tau of t is equal to 1 from minus tau to, so it is equal to 1 over 2 tau from minus tau to tau and 0 otherwise. Is a good family? Okay. So then what happened here is that you can see that I can kind of extend this function a little bit, right? So that basically what I'm saying is that this function is e power s of t0. So because the tau is going to 0, so I'm going to set this integral just from minus tau to tau. Is a good family because the 0 to infinity is like the 0, right? So it is like from 0 to tau. Is a good family. However, when tau is very small, if you take the limit from 0 to tau, it's similar from the limit from minus tau to tau, right? So basically, because minus tau is converging to 0, so that you take integral from 0 to tau, it's the same thing from minus tau to tau. And then you're going to take limit tau go to 0. In this case, you're just working with the function, this one divided by 2 tau of dt. Is a good family? Okay. So, but what is this limit? Well, you can see the denominator is going to 0, but what about the numerator? Well, it's kind of clear that the numerator is e power s multiplied by t, but the t is kind of restricted within minus tau. So basically minus tau less or equal to t less or equal to tau. But if tau is small, then e power minus s and t is very close to 1. Is a good family? Okay, so this one is very close to 1. So you're integrating basically something very close to 1 over 2 tau on the interval from minus tau to tau. So the integral is minus 1 over 2 tau multiplied by 2 tau. You're going to cancel. You're going to just have a 1 in the limit. So you're not going to have anything, but the limit is e power s multiplied by t0. Is that good, family? Okay. So, and this actually explains this line. Laplace transform of delta function is going to be an exponential function with a negative sign. So that's kind of a brief explanation of this line 20, how the Laplace transform of delta t minus a is equal to e power minus a of s. Is it good, family? Okay, so this is going to be a very important formula that you're going to look at later in your lectures. Is that good, family? Okay, so that's going to be the delta function t minus t0. So with that in hand, it means that you are really starting to be able, okay, so to kind of solve such differential equations with impulse force. Okay, so now let me show you one example. Okay, so let me show you one example. So here is an example. I'm saying that can you find a solution of such an initial value problem? So that's really we're studying to apply our theory to the initial value problems, right? So let's say which initial value problem that we are going to talk about. We're going to talk about this initial value problem. Okay, so we're going to talk about this initial value problem. So let's kind of put it here. Okay, so let's say we're going to quickly solve it. Okay, so we're going to quickly solve this initial value problem. Okay, so they're going to quickly solve this initial value problem. Okay, so we're going to look at it. And how do we solve it? Well, same thing. So you're going to kind of trying to do a Laplace transform of 2y double prime plus y prime plus 2 times y is equal to Laplace transform of delta of t minus 5. Right, so now we're going to, we have been already studying the Laplace transforms for differential equations many times, so we can be a little bit fast. So we're going to say that this is 2 times the s square of Laplace transform of y minus s of y of 0 minus y prime of 0, right? So that's going to be the first term, plus the Laplace transform of y prime is s Laplace transform of y minus the y of 0, right? So plus 2 times the Laplace transform of y is Laplace transform of delta t minus 5. But what is it? This is exactly what you're going to do on an exam. You're going to set a equal to 5. So that means the Laplace transform e power minus 5 times s. So that's going to be e power minus 5 times s. And you use the initial conditions. There's nothing here, there's nothing here, there's nothing here. So basically you get the relation 2s squared plus s plus 2 multiplied by the Laplace transform of y is equal to e power minus 5 times s. Is that good, family? Okay. Now, as long as you have this, it means that the Laplace transform of y is equal to e power minus 5 times s divided by 2s squared plus s plus 2. And you just want to calculate the inverse Laplace transform. So basically, it tells you that the y is equal to the inverse Laplace transform e power minus 5 times s of 2s squared plus s plus 2. But how are you going to find this inverse Laplace transform? That's going to be a question. Is a good, family? Okay. But then you can see that even from our previous lectures, we've been talking many times that every time you see a square, you have two options. One option is that you're going to decompose it into a product of two linear factors. That's the other the other proposal is that you're going to kind of complete the square. So here what do you want to do? Well, you remember that 2s squared plus s plus 2 can be written as 2 times s squared plus 1/2 of s plus 1. And then you can realize that you have no choice but completing the square. So that means you're going to write it as s plus 1/4, this thing squared, then plus 1 over 16, so 15 over 16, something like this. Is that good, family? Okay, so then you can easily see that y is kind of the inverse Laplace transform of what you just obtained. It's the e power minus 5 times s divided, right? So divided by 2 times s plus 1/4 square plus 15 over 16, right? So you get something like this. Now you can kind of pull 1/2 out because the inverse Laplace transform is going to be also a linear mapping. So e power minus 5 times s plus 1/4 square. I'm going to write as square root of 15 over 4. I'm going to write this squared. So now what you do? Well, you look at the table, right? So you want to find inverse Laplace transform. So you must look at the second column, right? So, but which term on the second column is going to work? Well, you should first look at 9 and 10, right? So 9 and 10 has a denominator, which is very similar, where you can take the a to be minus 1 over 4, and you take the b to be square root of 15 over 4. but you have an e power minus 5s, so what happens? Well, it's very simple. So if you let the capital F of s to be equal to 1, let's say 1 over, okay, so let's say s plus 1/4 square plus the 15 square root of 15 over 4, you set this one, then you're going to have the Laplace transform of f of t. Can you calculate f of t? Well, it's very simple. You can see that we can use this table. We can use line 9, right? So if you use line 9, then what happened here is that this one has to be the square root of 15 over 4. This is the b. And then the f of t is going to be e power, according to the line 9, is e power of minus 1 over 4 of t multiplied by sine of bt. So that's going to be minus 1 over 4 of t multiplied by sine square root of 15 over 4 multiplied by t. That's going to be the f of t. Is that good for everybody? Right? So that's going to be the relation. Now, once you have that relation, you can see that this function can actually be written as the inverse Laplace transform of e power minus 5 times s, let's say multiplied by f of s, but the coefficient is 1. So then you're going to have 4 over the square root of 15 multiplied in front of it. Is that good for everybody? Right? So then you can see that you're just trying to do e power minus 5 times s Laplace transform. You want to find this inverse Laplace transform. But what is this? Well, this is nothing but you must recognize that here you're going to use an exponential shift, right? So you're going to use an exponential shift. So when you use an exponential shift, according to our table, right? So according to our table, this exponential shift has to be kind of turned to an ordinary shift, right? So basically the a is equal to the 5. So you're going to do an ordinary shift. You're going to end up with the function ft minus 5 multiplied by ut minus 5. But you know the f is equal to this function. So that means you're going to have, let's say, 2 over square root of 15, because 4 over 2 is 2. And then you're going to use ft minus 5. So that means e power minus 1 over 4 of t, but you're going to replace the t by t minus 5. So that's going to be square root of 515 over 4 t minus 5 multiplied by ut minus 5. So this is kind of, you can see how synthetic problems can be in order to solve such type of problems, right? So we have been using the shift table of the Laplace transform several times in order to reach a satisfactory answer for our question. Is that good for everybody? Okay, so that's kind of not so simple answer, right? So not so simple answer where you have to use these specs. Is a good for everybody? Okay, so let me continue with the impulse functions from our next lecture. And so that's all I want to say for today's lecture. Let me continue till our next lecture. Okay, so that's what I want to say for today's lecture, and let us stop here.